Reviewing the engineering progress of the small electric aircraft, from selecting the battery and motor, choosing the airfoil, analyzing stability, determining the propeller, and performing theoretical flight performance calculations, to the final refinement and confirmation of the wing design. All the work we have done so far is to prepare for the next step, fluid structure interaction, and so on. So, why do we need fluid structure interaction? In all previous calculations, whether 3D or 2D, we assumed that the wing keeps its geometric shape unchanged during flight, but in reality, the wing, as well as other components, deforms under complex aerodynamic loads. For example, the wing vibrations you see when you're on an airliner are a form of aeroelastic oscillation. The way the wing deforms, and how much it deforms, directly affects the aircraft's aerodynamic performance, including parameters such as CL and CD. By considering fluid structure interaction, we incorporate all these real flight conditions to determine and verify the aircraft's actual aerodynamic performance. So, what is fluid structure interaction? Fluid refers to the aerodynamic forces determined by airflow speed and pressure distribution. Structure refers to the wing and fuselage stiffness, mass distribution, and modal characteristics, which determine how they deform and vibrate under load. Interaction means the fluid solver and structural solver exchange information and iterate repeatedly until both sides reach a stable equilibrium. For example, airflow causes the wing to deform, and the deformed wing shape then affects the airflow in return. This video will introduce the overall aerodynamic loads on the 3D wing and the verification of its aerodynamic performance. In the next video, we plan to compute the aerodynamic pressure distribution on the surface loads and provide aerodynamic data for the upcoming semi-coupled analysis. I have not conducted detailed studies on every part of the aircraft, so I plan to start with semi-fluid structure interaction, focusing on the wing. Semi-FSI means that aerodynamic forces cause structural deformation, but the deformation does not instantly feed back to update the airflow characteristics. First, for the model, I continued using the GA30U314 airfoil, with a wingspan area of about 14 square meters, consistent with the previous stability and flight performance calculations. Based on the optimized stability results, I also kept the -2-degree wingtip washout design, which improves stall behavior and reduces wingtip vortices and induced drag. In the model, the twist was applied in steps to ensure surface continuity. The wingtip was tapered by 80%, also following the initial design results from XFLR5. This reduces induced drag, lowers the lift at the wingtip, and allows the wing root to stall first, thereby improving stall characteristics. For the computation, I used the same environment as in the 2D case. Since we are considering the maximum loads and moments, the calculations use standard sea-level static pressure of 113,250 pascals and a static temperature of 288.15 kelvins. The flow is treated as incompressible, with a density of 1.225 kilograms per cubic meter. The gas constant R and the heat capacity ratio gamma are kept at their default values. Considering the propeller thrust at the motor's maximum power, the maximum level flight speed I previously calculated is around 50 meters per second. So here, I also set the airflow speed to 50 meters per second. Under ideal gas assumptions, the corresponding Mach number is about 0.147. At first, I made a mistake that caused the calculated CM to be consistently incorrect, When computing the overall pitching moment, I didn't account for the fact that the wing rotates around the leading edge axis. I used the quarter chord point for all angles of attack, but this is only correct and valid when the angle of attack is 0. There are two ways to fix this. The first is to keep the wing fixed and rotate the incoming airflow direction. The second is to shift the wing's rotation axis to the quarter chord line. Although the first method is more accurate in principle, given my current workflow, I chose the second one. This allows me to keep the CM reference point fixed at the quarter chord without worrying about changes caused by varying angles of attack. Since coefficients like CL are independent of velocity and depend only on the Reynolds number, and the Reynolds number variation in my project is negligible, I first compared the aerodynamic coefficients of the 3D model with those of the 2D airfoil section. One point to clarify: in 2D calculations, the airfoil section is treated as an infinite span wing, meaning no wingtip vortices and no induced downwash. This idealization will be reflected in the comparison of the results. First, we show the aerodynamic flow comparison between the tapered wingtip with washout and the untapered rectangular wing. From this, it is clear that the rectangular wing generates very strong wingtip vortices, which lead to high induced drag and poor stall performance. After the model optimization, the wingtip vortices are significantly weakened. Although they cannot be completely eliminated, the results align well with the previous theoretical predictions. For the CL results, because the 3D wing experiences induced downwash, while the 2D airfoil, approximated as having infinite span, has no wingtip vortices, the 3D CL values are overall lower. Since the 3D model uses a tapered wingtip while retaining the negative washout, the post-stall CL curve becomes noticeably smoother, and the angle of attack corresponding to CL max increases by about 3 to 4 degrees compared with the 2D results. Overall, this means the stall characteristics are significantly improved. In the CD results, the 3D model includes the induced drag that is absent in the 2D model, so the drag coefficients are higher at the corresponding angles of attack. Using the quarter chord point at the wing root as the reference for the pitching moment CM, I performed a linear fit on the CL alpha curve derived from CFD. From the slope relationship, the equivalent 3D aerodynamic center of the wing was determined and then compared with the previously obtained aircraft center of gravity position, located 31 millimeters from the wing leading edge. It can be seen that the wing's aerodynamic center lies behind the center of gravity. Finally, the computation also provided the total vertical and horizontal forces on the wing, namely the overall lift and drag, as well as the pitching moment at the wing root. These more accurate values can be used for basic flight performance validation. To prepare for the semi-fluid structure interaction, these overall forces need to be broken down through finite element methods into point-based loads, so they can be imported into the structural model with higher precision. In the next video, we will continue advancing the semi-fluid structure interaction workflow. Thank you again for watching. If you have any questions or suggestions, feel free to leave a comment. See you in the next episode.